Inside pretty much every piece of modern electronics, I'm talking everything from your phone to a satellite, there's this one component that's just a masterclass in precision engineering. So today, we're going to architect that little slice of perfection from the ground up.
So how do you even do that? We're going to pry open what most people think of as a black box, the operational amplifier, and you'll see it's not some kind of magic. It's actually a series of really clever solutions to some of engineering's toughest challenges.
So here's our goal, to really get the architecture of precision. We're talking about a device that's designed for massive amplification, pinpoint accuracy, and just incredible versatility. Let's see how it's done.
Okay, so challenge number 1. The real world is electrically noisy. You've got power lines humming, radio waves flying all over the place, and all of that is threatening to just completely drown out the tiny, precious signals we actually want to amplify. See, if we just amplify everything that comes in, we amplify all that noise right along with our signal. So the real problem is, how do you listen to a whisper in the middle of a thunderstorm? The solution, as you're about to see, is, well, it's just beautifully elegant.
And that solution is something called a differential pair. And honestly, this seesaw analogy explains it perfectly. Think about it. That unwanted noise, the common mode signal, it pushes down on both sides of the seesaw equally. So nothing happens. It stays balanced. But the actual signal, the ding we care about, creates a difference between the two inputs. And that tips the seesaw, giving us a clean, amplified output. Brilliant.
All right, next up, our op-amp needs a massive amount of voltage gain. And when I say massive, I mean over 100,000 times bigger. But how in the world do you pull that off on a tiny chip where every millimeter of space counts?
Well, here's a key thing you have to understand about chip design. Transistors are tiny and super cheap to make. Resistors, on the other hand, are relative giants. They're total space hogs on a silicon wafer. So the philosophy is simple. Just use transistors for everything. Instead of a big, bulky resistor, designers figured out how to use other transistors as active loads to get the job done in a fraction of the space.
So we build up this massive gain in stages. First, swapping out that resistor for an active load gives us a really nice boost. But for the truly insane gain we need, designers use this clever trick called cascoding. You can see it there in step 3. They literally stack a second transistor on top of the first one. This new transistor kind of acts like a shield, letting the first one operate in its absolute sweet spot, pushing the amplification to its theoretical limit.
Okay, but with all this incredible gain, we've kind of created a monster. Our super powerful amplifier is now living on a knife's edge. Any tiny little delay inside the chip can make it go completely unstable and start oscillating like crazy, turning our precision tool into a useless noise generator.
So, to tame this beast, we have to bring in the single most important concept in all of analog design, negative feedback. Think of it like a governor on a powerful engine. We're going to intentionally pull back the reins on some of that raw power to get something way more valuable. Perfect, predictable control.
So we make this amazing trade. We take a tiny piece of the output signal, invert it, and feed it back to the input. We sacrifice a little bit of that raw, untamed gain, but look what we get in return. The gain becomes stable and predictable, the signal gets way cleaner with less distortion, noise gets squashed, and suddenly the amplifier works great over a much wider range of frequencies. It's an absolute game changer.
But there's one more catch. Even with negative feedback, really high-speed signals can get delayed just a little bit inside the chip. And that delay threatens to turn our good, stabilizing feedback into destructive, positive feedback. To stop that from ever happening, designers add one tiny, crucial component, a capacitor, for something they call frequency compensation. It's like a strategic brake that slows down just the right part of the circuit to guarantee it always remains stable.
So, let's recap. We've solved the noise problem, we've figured out how to get massive gain, and we've tamed it with feedback. Now, it's time to put all the pieces together and see the modern masterpiece in its final form.
And there it is, the classic two-stage op-amp. And just look at how all our solutions click into place. Stage 1, that's our differential pair, killing that common mode noise. Stage 2, that's our high-gain engine, providing all the raw power. And that little compensation block, that's our stability control, tying it all together beautifully. It all just fits.
Of course, design never, ever stands still. For today's low-voltage electronics, where every last millivolt of power is precious, designers often go for something called the folded cascode architecture. It's a really clever rearrangement of the transistors that gives you even wider bandwidth and just better performance, especially when you're short on power.
So our blueprint is complete. But in the real world, an op-amp's performance isn't just one single number. At the end of the day, it's defined by a series of really critical engineering trade-offs.
And this is where the real art of engineering comes in, right? It's all a balancing act. You want a faster response time, what they call slew rate? Well, that's going to cost you more power. Want better immunity to noise from your power supply, or PSRR? That's going to add complexity and cost. And then there's the most famous trade-off of all, gain versus bandwidth. You can amplify a signal a lot, or you can amplify a wide range of frequencies, but you can't have the maximum of both at the same time. And that, right there, is the key takeaway. Once you understand how these individual building blocks come together to form a whole system, and you get how all their trade-offs are balanced, you're not just analyzing circuits anymore. You're architecting them. You're a system designer.
So, you see, the op-amp isn't some magical black box. It's a testament to brilliant engineering, just a set of elegant solutions to really fundamental challenges. We've just walked through the blueprint for precision, so the only question left is, what are you going to build with it?